while it's warming up, I'm going to kind of try to describe the concept of restoring division to you. So today what we're going to learn about is we're going to learn about two types of division algorithms. One is called restoring division and one is called non-restoring division. And the reason I'm presenting two different algorithms is because this is a good case of the concept of good design requires good compromise. And so restoring division, basically we're taking two n-bit numbers in, right? And we have to get some sort of, so let's say we had, let's go back to elementary school. So you have 8 divided by 5, right? So how are we going to represent this solution? Yeah, one of the remainders is very simple, right? So we have to do these two numbers physically. So we have to do 0, 0, 0, 1 and 0, 0, 1, 1. Okay? So we basically have to figure out what we're going to call this a remainder, and we have our quotient, and we have divisor and dividend. So basically, the divisor is the one that does the acting, right? So we go back to our English verbs. So we have the divisor and we have the dividend. And then we're going to try to, what's going to happen is we're going to go back to that whole idea that we were talking about at the beginning of the semester about, where's the ONOFF button? How did that not turn it off? Yep. Would you like to turn the system on? Yes. Laptop. There we go. All right, so basically what I was stating here, we have one remainder of 3, and we have to physically represent these, right? And so we have our divisor and our dividend. So those are our two inputs to our algorithm, and we have two n-bit inputs. So in this case, this would be 1, 0, 0, 0, and then you have 0, 1, 0, 1 as our two inputs, divisor and dividend. And so we're going to go back to, remember we're talking about Thomas Hobbes talking about arithmetic, and that division is just subtraction over and over again. So what we're going to do is we're going to be doing bit shift, we're going to be doing a subtraction, and then if we have a 1 as the most positive number, what we're going to do is we're going to do something called a restore. And what that means is that we don't want, okay, so the restore means that at that stage we have a remainder that starts with a 1. So why would a remainder starting with a 1 be bad? I can hear mumbling. Somebody say it confidently. Yeah, it would be a negative number, right? So you can't have 8 divided by 4 is going to be, or 8 divided by 5 is going to be 1 with a remainder of negative 3. That's right. That's not the way. That's not the convention. So the way it starts is we're going to initialize a remainder of n plus 1 bits, and then we're going to initialize our quotient by setting the quotient equal to the dividend. So what that means is, let's kind of start out. We have our 8 divided by 5 is our sample that we've been putting in here, right? So we set a 5-digit remainder, or n plus 1. So if it's 32 bits in MIPS, it's going to be 33 bits, right? So we have a remainder that starts out as 5 bits here, as all zeros. And then we initialize a quotient that's equal to the dividend. And we're going to set mantissa of n plus 1 as equal to the divisor. So that's another term there for mantissa. So we're going to do this 5 bits. So we take in this divisor here, and it'll be 0, 1, 0, 0, 0. And that's going to be equal to the mantissa. So for I equals 0 to n minus 1, what we're going to do is we're going to left shift the remainder, and the most significant bit of the quotient becomes the least significant bit of the remainder. So what I mean by this is This most significant bit's going to pop off. This will be the remainder. We are missing the bit here. We take this bit and move it over there. So then the most significant bit of the quotient is going to become the least significant bit of the remainder. So this shifts over. So then our result's going to be 0, 0, 0, 0, 1. And then our quotient is going to be, our new quotient is going to be 0, 0, 0. And we're going to have a bit here that we're going to be missing. So it's kind of working in the same shifting principles as our multiplication algorithm, right? And then we're going to subtract the mantissa. So in this case, our mantissa was equal to our divisor. So we had 0, 1, 0, 0, 0. We do the 2's complement. That becomes 1, 0, 1, 1, 1. Add 1. That becomes 1, 1, 0, 0, 0. So then you're going to plus 1, 1, 0, 0, 0, right? And then you're going to add it here. So it becomes 1, 1, 0, 0, 1. Now this is where, let me change the color here so that way I can emphasize this. This part of the algorithm is where people get confused the most. So I'm going to act it out right here, and then I'm going to be hammering it in when we do both restoring and non-restoring division. We're going to left shift the quotient, so we've already done that here because we've left shifted it and we have a missing. And the most significant bit of the remainder, which is this guy here, is the negation of the least significant bit of the quotient. So what does that mean? If it's 1, it should be 0. And if it's 0, I want it to be a 1. When I was an undergraduate and I took this course, when I did this, I always made it a habit of drawing it here. So I'd have a 1, and the red here. And then I would actually write it over and then make a little negation mark there to remind myself.
So do you actually, so that's all that stuff you left shift and you store a bit?
Yes.
Do you mind if I write that over?
There's Alex Gunter overthinking the problem again. Most significant bit of the remainder becomes the negation of the least significant bit of the quotient. So you've done a bit shift to the left shifted the quotient, which I represented here already. And the most significant bit of the remainder is negation of the least significant bit of the quotient. And then, if the most significant bit of the remainder is 1, we're going to restore, meaning we're going to add the mantissa. So then in this case, it would be 0, 1, 0, 0, 0. Now, this is where students make a common mistake. If I'm subtracting 8 here, and I'm adding 8, what's this value going to be? So much overthinking. If I have 1 up here, and I subtract 8, and then I add 8, what's the value going to be? 1. Very good. So, common mistake is you try to think through this addition on an exam when there's pressure. No, if I've subtracted 8 and I'm adding 8, don't even bother going through it. Just write the original number, right? So that's the common mistake. So that is one iteration of our algorithm here. Does that make sense? Now, if it's 0, we don't restore. And so the example that I'm going to give here in a second will be an example of where you have to do both, make that decision. So if it's 0, do nothing and move forward. Okay. So does this make sense so far, this algorithm? All right. So in this case, what we are going to do is we are going to find 8 divided by 3 using restoring division. So we set our remainder to 0. It's an n plus 1 bits. Our quotient is going to be equal to our dividend, right? And the mantissa is going to be equal to the divisor. So in this case, it's 8 divided by 3. So 8 is 0, 1, 0, 0, 0. 3 is 0, 0, 0, 1, 1. Divisor, dividend. Divisor is the quotient, and the dividend is the mantissa. So the way I always set this problem up, I found this is the easiest way to do it, is to just have your remainder and your quotient next to each other. So that way you can represent it and see it in bit shift form. So I can zoom in a little here so you all can see. But here's how I would draw out the first stage. So this R, comma, Q, remainder quotient. So you have some sort of register where you have the number of bits, which I think what Alex's start was alluding to. You're performing a bit shift. So you have initially 0, 0, 0, 0, 0, and then 1, 0, 0, 0. And the way I describe my algorithm is you left shift the remainder, and then the most significant bit of the quotient becomes the least significant bit of the remainder, which is how we ended up with this 0, 0, 0, 0, 1 and 0, 0, 0, 0 and blank. Does that make sense? So you've got to perform this bit shift. Then, in restoring division, you subtract the mantissa every time. So in this case, 3, 1, 1, 1, 0, 1, which is how we got this number here. And this becomes 1, 1, 1, 1, 0. Now, the most significant bit is 1. So what does that mean? There's two things here. Yes, Travis? Yep, the most significant bit of the quotient becomes the negation of the least significant bit of the remainder. So that's how 0 is there. And by the way, here's something to recommend on the exam. You know what 8 divided by 3 is going to be. It's going to be 1 with the remainder of 2, right? So see, we have, 2 with the remainder of 2. My apologies. So 2 remainder 2, and you should have the negation stages should be the opposite of here, right? So you're going to know that this is going to be 0, 0, 0, 1, 0, right? You see that? Which means, let's say you complete the algorithm before we go to any other steps. You complete the algorithm and you have a wrong answer. You're expecting 2 remainder of 2 and you get 1 remainder of 4 or something weird like that, right? If you do it like this, you will be able to see, so if we had 1 remainder of 4, this would mean it would be 1, 0, 0, 0, right? Which means your error occurred in your second cycle. Does that make sense? That's a good way to troubleshoot and figure out precisely when it is you made your mistake. Because what ends up happening is this can be a little heartbreaking as a professor. You see a student have 95% of the right answer, they get the wrong answer, and they erase the whole thing. I can't count it if you erase it. Oh. But sometimes I try to help out in that situation. But when it's fully erased, you go, oh no. So try to help you out here. Okay, so then we did our negation here, right? So what's our last step? Because it starts with a 1, we restore, and you just rewrite it. Don't bother trying to do the addition there. So that in the algorithm there was this step. Second cycle, again, left shift. Most significant bit of the quotient becomes the least significant bit of the remainder. So now we have 0, 0, 0, 1, 0. We subtract the mantissa. And then we get 1, 1, 1, 1, 1. The negation of the most significant bit becomes the least significant bit of the quotient. So you can see here 0, 0, 1, 0. That's our solution. And then because it starts with a 1, we restore again. In the third cycle, we do the same thing. So we have, this is our mantissa. We left shift. This significant bit goes away. The most significant bit of the quotient becomes the least significant bit of the remainder. You have 0, 0, 1, 0, 0. We subtract the mantissa, and we get 0, 0, 0, 0, 1. Most significant bit of the remainder is negated and becomes the least significant bit of the quotient. Now it starts with a 0, which means we do not restore at this stage. See how I didn't do this plus m here? That's the decision there at the end of the algorithm. And then we go to cycle 4. We subtract them, we left shift. So it becomes 0, 0, 0, 1, 0. Which, by the way, at this cycle here, in the last cycle, when it begins, you should have, when you do the bit shift, you should have the solution already for the quotient. I'm sorry, for the remainder. Right? If it starts with a 0. So here, we subtract the mantissa. We get 1, 1, 1, 1, 1. The negation of the most significant bit becomes the least significant bit of the quotient. So we have 0, 0, 1, 0. We have our correct solution for the quotient now, right? So then, but we still have 1, 1, 1, 1, 1. We restore because it begins with a 1 here. And therefore, we added, went back to 0, 0, 0, 1, 0. And therefore, we now have our remainder is 2. So therefore, our quotient is 2, and our remainder is 2. I'm sorry. Quotient is 2, and our remainder is 2. Does that make sense? Yes?
How do you know how many cycles you have?
We define it in the, it should be n, the number of bits. And as I stated for multiplication, I limit myself in the same way. You will not have more than 4 on it. Yes? The minus, we do it every cycle. So in the algorithm here, for 1 through n minus 1, so we do 4 iterations, so we do n iterations, so it's 4. Every cycle, no matter what, the first thing we do, we left shift the remainder, and the most significant bit of the quotient becomes the least significant bit of the remainder. And then every time in restoring division, remainder minus the mantissa. And for those of you who are familiar with, how many, you all know what minus equals is? I should make sure of that before I start throwing out pseudocode if people don't know what I'm talking about. Okay. Any other questions on this? So what we're going to do next is we're going to compare it to a different algorithm called a non-restoring division. So in this one, we subtract the mantissa every time. In non-restoring division, we make a decision based on whether or not it's a 0 or 1 at each iteration. The objective is, for most cases, to make it run faster. But as we're going to see, there's some cases when it won't. So this is a good example of good design requires good compromise. So we do the same thing. First 3 stages are the same, exact same. And then we get 4 iterations, in this case when n is equal to 4. First step, we do the exact same thing. Left shift the quotient, and the most significant bit of the quotient becomes the least significant bit of the remainder. So here, what we're doing instead is, if the most significant bit of the remainder is 1, we're going to add the mantissa. Else, if the most significant bit of the remainder is 0, we're going to subtract the mantissa. And then we do the same thing where the left shift of the quotient, where the most significant bit of the remainder is the negation of the least significant bit of the quotient. Now, in a good number of cases, this will run faster than restoring division. However, in the case when the most significant bit of the remainder is 1, after the completion of the algorithm, so the 4 stages are done here, right, in that bracket. So if you get to the end, and the most significant bit of the remainder is 1, what does that mean? What was that? I heard it. Yeah, so you have to add the mantissa, and why? What does at the end of, when you have the remainder as a starts with a 1, what's important about that? Why do we have to restore there? Yes, exactly right. Very good. Because we have our algorithm has produced a negative number, so we should restore the mantissa, which will give us the positive number. So in that case, the algorithm will take longer, but in most cases it won't. And we're going to go through an example. Actually, it's going to be the same thing, 8 divided by 3. And you'll be able to see the difference. So if you're a little confused as to why, as to restoring versus non-restoring, my recommendation, and this is perfectly acceptable on your homework, do the example side by side. When you're preparing for an exam, do this same problem, 10 divided by 4, 6 divided by 3, whatever works. Do them side by side and work through the algorithm together where you can see the difference. Does that make sense? So we're going to go through that here in a second. So again, this is where the algorithm is different. In restoring division, we always subtract the mantissa, and then we add if and only if that remainder is 1, but that's every cycle, right? Here, we do that only once at the end, but that would require an additional cycle. So then you return the quotient and the remainder. Okay, so here is our example about, nope, that's right. Example 2.7, this will be, I believe this is the end of section 2, yes. Finding 8 divided by 3 using non-restoring division. So we start out the same way. We had 0, 0, 0, 0. We know the quotient is 1, 0, 0, 0. We know the mantissa is 0, 0, 0, 1, 1 because it's 3. And we know the negation of that complement is 1, 1, 1, 0, 1, right? So far, the same thing. We get to the first stage. We have 0, 0, 0, 0. Least significant bit. This was initially 1, so that came over here. So we have 0, 0, 0, 0, 1. Now it starts with a 0, right? According to the algorithm, because it starts with a 0, we subtract the mantissa. So that means we're actually so far kind of doing the same thing. 1, 1, 1, 0, 1. And that gives us 1, 1, 1, 1, 0, like we have here. The most significant bit of the remainder becomes the negation of the least significant bit of the quotient. So far, we have it right. We do not have to restore because it's non-restoring division in this case. So cycle 2, we left shift the remainder. So we had 1, 1, 1, 1, 0, right? We left shift it, so it becomes 1, 1, 1, 0, blank. The most significant bit of the quotient becomes the least significant bit of the remainder. So we have 1, 1, 1, 1, 1, 1, 0, 0. In this case, it starts with a 1. So we add the mantissa. So it becomes 0, 0, 0, 1, 1. Then we get all 1s. The most significant bit of the remainder becomes the negation of the least significant bit of the quotient, which is what we have here. That should read 0, not 1, 0. My apologies. See, this right here, that is correct. That should read 0, 0, 0, 0. Does that make sense? Stage 3. See how I'm explaining it faster, so it's actually kind of running faster in the processor? You can actually feel it in how I'm teaching it. So left shift the remainder. Most significant bit of the quotient comes here, so it becomes 1, 1, 1, 1, 0. Because it starts with a 1, we add. Now it becomes a 0. That bit goes away. We do not consider, this is the common question is we do not consider the carry bit over here. So just whatever happens to be in that n plus 1. So here it's a 0. The most significant bit of that solution is flipped, and becomes 1 here, right? And then we get to the fourth stage, we do the same thing, left shift, most significant bit of the quotient, least significant bit of the remainder, that becomes here and these, so this one flip shifts over, so it becomes 0, 0, 0, 1, 0. It starts with a 0, so we subtract. So now we have 1, 1, 1, 1, 1. Most significant bit becomes the negation of the least significant bit, which is this bit here. So then we get, so now we have our solution, which is 2 for the quotient, which is correct, and negative number, negative 1, which is not correct. So in this way, you're adding negative 1 and 3, which is going to give you 2, right? So it actually, the solution is going to come out right. So this becomes 1, 1, 1, 1, 1. In this last step, we have met our condition. So we had 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. You see the difference? So the non-restoring division, the objective is to make it run faster in most cases. But here we have a case where it didn't work out. Does anybody have any questions about restoring and non-restoring division? Travis says no. He speaks for all of you. Okay. So on that note, we're going to go to section 3. So I'm doing this in a little bit of a different order than in your textbook. So for those of you who asked me about trying to review the textbook to gain additional concept, this is actually, you'll see a lot of what I'm presenting here in chapter 5. The reason I'm presenting it this way is because we're actually going to discuss the physical details of the registers and the memory hierarchy so you can physically see what loads and stores are. My first time I taught this here, I was told that everybody knew C, and I quickly found out that that was not the case, and I taught it that way, and everybody looked horrified, like, what is that? What are you doing to me? So, and the thing that's different from C than Java, for those of you taking C++, you're familiar with pointers, right? So pointers can be nasty little things if you don't work on them correctly. But a lot of people had only taken Java, so I started throwing out pointers and doing, and oh God, what is that? What is that star thing? Why is it making my life miserable? So we're actually going to physically describe what a pointer is, and then we're going to go into C code. And you'll learn just enough C code to be able to understand the whole compiler-driven encoding of the microregion. So if you recall from one of the TGOs I had here, data may only be operated in a register or in load store accesses. Repeated use of registers as basic blocks of code prevents redundant load stores. So in this section, we're going to learn why that's bad, and we're going to try to make these faster computations in the registers work better. So TGO 3.1 is answer a question that probably a lot of you have, which is what exactly is a register? Let's see if I can get this just a little bit. There we go, good. Registers store bits of information in such a way that systems can write to or read out all of the bits simultaneously. So the way it works is you're going to have 32 SRAM cells. So let's say you had 4 SRAM cells, and you're going to have either a write or a read line. And the registers allow all 32 of these to go out simultaneously, and that becomes important, especially when we get to the Kane stuff. We start talking about static timing analysis. You have to be able to make everything work in a certain clock cycle, right? So you want everything to come out rapidly and work at a specific time, so that way you can make the processor work efficiently. So in MIPS, we have 32 bits, so therefore we have to worry about all 32 going out at the same time. Now, to recall from the first lecture, I went this whole thing about instruction fetch, instruction decode, execute memory, and write that, correct? So in order to actually determine which registers we're going to use, we have to actually know the format of a MIPS instruction. So it's broken down as such in 3.2. The first 6 fields, the first 6 bits are known as the opcode or operation code, the basic operation of the instruction. It's an R-type instruction. Is it a branch instruction? Is it a jump instruction? I'll be teaching you all of those in the next section. RS is the first register source operand. Register source. RT is the second register source operand. So if we have an addition, the opcode is 0, and then RS would be the next 5 bits. And does anybody remember why we use 5 bits to represent a register in MIPS? Why do we use 5 bits? No, but you're on the right path. If I want to write a register address and I have a 5-bit value that I can use to register to indicate that register, what does that mean I have? Up to 32 registers. Very good. You're on the right path when you said 5 instead of 32. But that's how you do shift amount, actually. The shift amount becomes a 5-bit value that represents a 32-bit value that you can shift, and then you actually do what's known as a 5 to 32 decoder. Y'all remember decoders from 235? Yes? No? Lots of no one answering. Okay, so then the destination register. So you have 2 additions. So 2 values that you're going to add or subtract, do some sort of operation on, and then you're going to store the result in this RD, right? The 5-value shift amount is there, and then function is this next 6 bits. If you recall from section 2 where you did that topical guide objective, where we were talking about the inputs from the function contribute to the actual operation of the ALU, right? So that's coming from here. So we have something coming out of instruction memory, and then that goes to the ALU controller, right? It does all that logic that you came up that I gave you guys, and then it actually tells the ALU what to do. So now we're starting to build our advanced digital system up. And so there are 3 instruction formats. The 6 that I gave you here are what's known as a register instruction. By the way, I should do my little thing here. You will see this TGO again. Registers are used for instructions to perform an operation on 2 register values and places that result in a register. So I have 2 register values, RS and RT. Those are my 2 source registers, correct? They perform some sort of operation and then store it in RD. They will perform that operation in the arithmetic logic unit. So they use it, all 6 of these. Opcode is 6 bits, and opcode is always going to be 6 bits for all 3 of these instruction types. We have our source and destination registers, the shift amount, and the function. So an R-type instruction would be a shift amount. So let's say I want to multiply a number by 8 for some reason. And you're going to want to do that in the future. Okay. If I want to multiply a number by 8, do I want to do this? We've just gone through this complex multiplication, right? We've done this complex division. Is there a faster way to multiply by 8 in binary than using our multiplication algorithm? Exactly right. So I would set shift amount to 3. Very good. So you can do it in 1 cycle instead of doing it in 4. So our immediate, we have RS and RT. So in this case, RT is a destination register. I really feel the book will have RT there, but I think they should have used RD because in most I-type instructions it's RD. But you can also use it for what's known as a branch instruction, where we can compare them, any if statement where you're using to determine whether or not you want to do the code or not. It's known as a branch, but we'll get there in a second. And used for data transfer instructions. So a classic I-type instruction would be F equals A plus 6, right? So I have one register, I have a source register, and then I have a destination register. And then I have this number 6, which is represented in a 16-bit immediate value. So there would be 13 zeros and then 110 representing 6. So here's a question. If this was 16-bit number, I could have F equals A minus 6, right? So if I knew that, what could I do for the 16-bit number there? To reduce the complexity. To give you a hint, compiler-driven encoding of the micro engine. This is where this comes into play. Any ideas? It's on the tip of your tongue. You saw me circle the. No, you would. Okay, you're on the right path though. So what we're going to do here, we're going to add -6. So we're going to put the compiler will make this -6 in the number, and we're going to add -6. So the reason why that benefits us is because when you have your control unit is based on taking that 6-bit opcode and the 6-bit function and decoding it and being able to do it this way, right? So we have add, we have subtract, and we have an add immediate. But because the compiler can make this a negative number, if you actually look at your MIP screen sheet in the front of your textbook, there is no subtract immediate instruction. That's because it allows you to reduce the size and the complexity of your data path. Very good. And then jump, basically, so if you have you remember you have a function, so you have function, we'll call it function foo, int foo, right? And then we had int a. And then we have some sort of stuff, and then we turn b, which is something that resulted from a, right? So that we call foo in main. We call foo in our main function. So we do the function, but we have to get back to main, right? So physically, in the instruction memory, what's physically happening here, and jump is defined as jump to a new address, right? So we have this instruction memory, and the main is these instructions to these instructions, right? And then you have a set of functions, and foo, let's say foo is here. So we get to a certain point where we call foo. We're actually going to jump here. So the jump indicates the exact number of that instruction. Go to this instruction. Then we complete it, and then we're going to jump to the instruction after the function call, right? Because we want to actually be able to continue the function, the main function. So that's what jump instructions do. They allow us to jump from one instruction to another in order to be able to complete the function as dictated. So, yeah, that happened on the next page. Okay, so, did I want that? Yeah, I'll leave it as a TGO because that's a very common student mistake. All right, so I included 3.4 as a TGO because people often get confused about the RT and the I-type instructions. So I defined this out here. So RS is a source register for all R and I-type instructions. RT is a source register for R-type instructions and is a destination register for I-type instructions. And RD is a destination register for all R-type instructions. So this is here to reinforce a concept that I've seen students get wrong on exams. so what we're going to cover next, give your textbook on you, please. So there on Blackboard, for those of you who do not have a textbook, I have posted a copy of what's known as the green sheet. So the green sheet is on the first page of your textbook. This got it. Thank you. Let's say I'm going to ruin everything with book. So there's this green sheet in the front here, right? Some of the things that I'm showing you are here in the book. So I'm going to show you some examples. But the next thing we're going to go is the register names, numbers, use, and call convention. It's down here in the bottom right corner. All of the instructions, the add format is R-type, and it's going to tell you the operation in Verilog, which you'll learn later in the semester. Register RS plus register RT is equal to register RD. And it gives you, it says here, function opcode slash and hex, so you can actually determine the exact value of the function. So all of this is available to you. It actually shows all the opcodes. It shows the memory allocation, how that's done. And IEEE 754 format, the equation's right here. And then you have your symbols, and it actually tells you the max and min value. And so this, the big green sheet, which will be provided for you on all the exams, is basically this sums up the whole textbook in one page, and then the rest of the textbook tells you how to make sense of it. So, thank you. So this 3.5 here, you're actually going to see it in the MIPS green sheet, both on Blackboard and in your text. So the number refers to that 5-bit value, right? It's from 0 to 31. So when you have a value in one of these register instructions, it's telling you to get these specific registers. So we actually are going to reserve register 0 as the value, constant value 0. And that'll actually become very important, especially when we start getting into branches. So we have an assembler temporary value. So what's happening here is that we have some sort of temporary value that is reserved for your compiler and your assembler. So you compile the code down, and then you actually have assemblers, assembly language, which that assembly language is kind of what I'm referring to. It's the same thing that's in Verilog, where you have add, S2, S1, and S3, right? That's assembly language. So V0 and V1, these are values for function results. Remember, I was just giving you the example of a function. You have to have a jump instruction to tell you where to begin, but you need to have some sort of, so you call it int foo, right? We actually have these two registers saved specifically to store the results of a function. So you say add, so if it was like b equals a plus 5, we have to turn b, right? So you would say v0, you could say add v0 for our sum. Add v0 would be our sum. And here we have arguments a0 through a3. So a0 would be our argument a, and we pass that function. So it would be, if we pass two functions, a0 and a1, right? That would be the same thing as add. So v0 is 2, right? So that would be register 2. a0 is register 4. And a1 is register 5. So that's what's physically going on there. The actual, if we were then take this out and go through our whole R-type instruction, we know that add, the opcode is 6 zeros. We would know that our source 1 is A0, right? So that'd be 0, 0, 1, 0, 0 for RS. For RT, it's 0, 0, 1, 0, 1, so that's RT. RD, our destination register, is 2. That'd be 0, 0, 0, 1, 0. Our shift amount is 0 because we're not shifting anything. And 20 hex is add in MIPS. So that'd be 100000, right? So that's 20 hex. Y'all recall how to convert from hex to binary? Everybody's feeling a little down from last night. Is that what's going on here? It happens. So these are for functions. So 8 through 15, T through T7, and we're going to see it again here, T8 through T9. In our function, we're going to do a lot of what's known as temporary values. So we can only add 2 values and store it in a register. So let's say I have some code, f equals a plus b plus c, and so the save temporaries refer to actual variables, right? So we'd have f is going to be s0, a is going to be equal to s1, b is going to be equal to s2, and c is going to be equal to s3, right? And we're adding these 3 together. What would be the problem with doing this? So we have S0, S1, and S2, right? So we're taking A and B and putting it in F, and then we're going to add F plus, and this is S3. So here what I've drawn out here is F is equal to A plus B, and then F is equal to F plus C. What would be the issue with that? Given my initial F equals A plus B plus C. Why is this problematic? Any ideas? What's my initial line of code? Let me say it. Y'all should say it. Come on, wake up. It's okay. Chad Kelly can't hurt you here. Hey, what's the line of code that I wrote initially? F equals A plus B plus C, right? And what's the code that I wrote here at the bottom that we converted in assembly? F equals A plus B and F equals B plus C, right? Why is this bad, given this? There we go. It's starting to click. The coder never told you to make F equals A plus B, right? So the compiler will do what you tell it to do. I know that sounds, for those of you who've worked on coding projects, and you go, why are you doing that? I promise you, the compiler does what you tell it to do and what you tell it to do only. You can't put F equals A plus B because, one, that's never what the code did. And what we're going to find out is that when you have to deal with parallel processors, those intermediate values become important. You have to maintain the integrity of the value. So in this case, how to get around that is we use these temporary values. So we say T0 is equal to S1 plus S2. And then we say S0, which was initially F, is equal to T0 plus S3. And then when we're done with T0, we can overwrite it all we want because it was just a temporary value. We only need it there as a placeholder. Does that make sense? Okay, so we're 20. And then we'll, in later sections, and when we get to multiprocessing, this K0 and K1, 26 and 27, reserved for the operating system's kernel. This is what we're going to be dealing with when we deal with exceptions and overflow. What happens when your data path produces a result that cannot be represented by the 32-bit architecture? You have some sort of overflow or an exception, meaning that let's say it actually produces the wrong result, we can prove it. Or let's say your compiler generates an instruction with an opcode that doesn't exist for some reason. It's screwed up. The person who wrote the reason why you have the architecture is because you have to add levels of security at the software and the hardware to ensure it works properly. So let's say you come in, you have some compiler coder who writes bad compiler code, and you run it on your data path, and it produces an opcode that doesn't exist. What do you do? you have to tell, you don't know the answer to that, next time I taught you. You have to tell the operating system that doesn't work, right? The operating system manages everything. Remember that very first day where we had these levels of abstraction? You have to tell the operating system, hey, somebody screwed up here. This code sucks, right? And if you keeps going and keeps going and keeps going, eventually you get the blue screen of death, right? That's what's actually going on here. The blue screen of death is telling you that you have found some sort of memory element or some sort of instruction or some other, try-catch that didn't work. And you got all the way up past the operating system. And that's the way of telling you somebody sucks at coding. Okay? And it wasn't you. But that doesn't mean that that assignment that you were working on is any less done, right? And so global pointer, stack pointer, frame pointer, return address. What was it? Computer science. What's the computer organization that you have to take in assembly language? You have to take that. By the time you're done with this course, you get to that course. You go, yeah, I know all this stuff. We're good. But for right now, just I believe button. The general idea is that when you run some code, you have to have some frame pointers, global and stack pointers in order to keep it within certain memory elements. And then the last thing, return address. You can store when you have a function and you need to jump to your return address, meaning I need to get to this in order to compute the code. We put it here in register 31. So that's the 5-bit when we were talking about RS. Sorry, I got to sort someone was humming. When you have that 5-bit value, it actually refers to all of this. Does anybody have any questions about that? Okay. So what I was kind of referring to is here. So we have the instruction to add. In the code, it's like this. It actually states the format. So this is from the MIP screen sheet, right? So for every instruction, it has something like this. So the operation in Verilog, so you have register RS plus register RT. You add them together in the arithmetic logic unit, and you get RD. So it also says opcode / function in hex. And so what this means is 20 hex is 100000, and your opcode is all zeros. And in, let me go here. So if you go on Blackboard, and you go under, where are you, 385, and you go under Content, when it decides it actually wants to do it. Reference files. So here's your MIP. I've included the MIP screen sheet. So you can actually see on here all of these different instructions. So here we have add. I've included add immediate. And I brought this up specifically because I want to show the difference between an R type and an I type in here. So R type, we have, it says sign extension immediate. So that was our 16-bit immediate value. Plus register RS is equal to stored in register RT. Now here, this is a common question. People see this and get confused. So let me clarify what this means. So opcode / function in hex. If it's an I-type instruction, there's no function. If it's a J-type instruction, there's no function. Remember, the function is the 5-bit, it's the 6-bit value at the end of the instruction for R-type. So if you have both, that means it's opcode / function. If you only have one of them, it's just the opcode. So the opcode for add immediate is 8 hex, right? So it's 001000. So that's 8 hex. You have to have 6 bits. So if it's just 8 hex, that's what you have. So in this case down here, branch on equal, what that means is if it's going to compare these two values, and if they're equal, it's going to go to a specific instruction. That opcode is 4 hex, so it's 000100. And here you have load word is 23 hex because it's an I-type instruction. We'll go into all this later in this section, but you get the general idea. Yes, Alex.
For R-type instruction, it's listing both the opcode and the function.
Okay, so correct. Mm-hmm. Yeah, so. Oh yeah, R-type instructions are all zeros. Yeah, for every that's a good observation, Alex. So for R-type instruction, the opcode is always 0. See, it's 0/0/0/0/. It's always 0. That's why we need it. So that's why I introduced that topical guide objective where I have the comparison in the ALU. You have to send the function value, because if you get 0, it's going to indicate that it's an R-type instruction. Okay, so I alluded to this a little earlier. Byte addressing. Let me scroll up here a little bit. All right, so byte addressing. What this means is that I have, actually I'll just draw it up on here on the screen. I have some sort of block of memory, right? So this is where we get into the computer architecture, memory addressing versus memory technology. The memory is broken into 8-bit chunks. If I need 32 bits, what happens is I point to a specific 8-bit, and when I get when I get a store word, I get that one plus the next 3. That allows me to get 32 bits, right? If it's word addressing, you get 32 bits. But in this case, MIPS uses what's known as byte addressing. An index that we use to calculate a pointer is known as byte addressing. Byte addressing means that we can point to the index, points to a byte, 8 bits of memory. And in this next one, I will make very clear what I mean by that. So there are 5 types of memory addressing in MIPS, 5 types of specific. So this is why knowing this is important. So an immediate is just the operand is a constant within the instruction itself. Right? So we have some value here. The immediate addressing means that A equals B plus 5. 5 is actually stored in the instruction, right? So that's where the address is. It's actually in the instruction. You don't need to go anywhere else to find it. So we find immediate. The operand is a constant within the instruction itself. So for the TGO, I say define the 5 types of memory addressing and draw and represent them with a drawing. So that's what this is here. So the drawings are required. So register, let me zoom in on register here so you can all see what's going on here. So register, the operand is a register. So you have the opcode, the register here. This is RS. So here's what I'm drawing. So I have /5. That is indicating that it's 5 bits. Then I have, this says 5 to 32 decoder. So this actually produces a 32-bit line in which one of them is going to be 1 and all of the rest are going to be zeros. So in that case, the one that's 1 is going to actually read and produce those 32 bits on the output. Otherwise, when it's 0, it'll just leave them alone. So that's why we have a 32-bit decoder. So basically, we'd have 00101. That indicates 5. We go in there, and it's 0, 1, 2, 3, 4, 5, and then the rest of these are 0, right? So when they all go through here, it says, hey, do I want to read you? No. 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 Do I want to read you? Yes. Gives me that value, and it goes. And then that actually goes to the register itself. So this says register. Does that make sense so far? Okay, so the next one, let me zoom out here, and I will read it, and then I'm going to zoom in here because this is kind of an important concept. Base addressing. So this is how we do loads and stores. This one here. You will see this over and over again. This is the physical manifestation of a pointer, for those of you who had C++ or C. Base addressing. The operand at the memory location whose address is the sum of the register and a constant in the instruction. So if we go back to our MIP screen sheet, we're going to see that load and store instructions are I-types. The reason why is because the register RS is going to store the value in memory of the base pointer of an array. So y'all dealt with arrays, right? Okay, so you have so we just say a of 5, right? So we have some sort of block of memory of which this is where A0 is. So we use A1, A2, A3, A4, and A5, right? So register RS, so we do our RS value, we go here, 5 to 32 decoder, and we get that value here. This value here is pointing to where A of 0 is. Does that make sense? So it's pointing to A of 0. I know where the beginning of the array is. If you think of an analogy, you're going to your friend's house, right? And you turn down their street. If the GPS goes, turn right, left here, you turn left. Where the moment you turn left, that's where your base pointer is. We define that as the base pointer. That's the beginning of the street. And what you need to do, so if it starts out at house 1000 and you need to get to house 4000, right? So there's 4000, there's 4 blocks. It tells you how to get there. You know I need to go 4 blocks in order to get to the specific location. That is the immediate value. That's how far down I need to go down the street. So this is where the street is. This is how far I need to go down the street. It's an I-type instruction. So you see 3126, 2521, 2016, 150. So we do this thing here, and we'll call it a sign extension. I think I've alluded to it before last lecture, because this is 16 bits, and our arithmetic logic unit has two 32-bit inputs, right? So sign extension means if it's the most significant bit is a 0, I just add 16 zeros to it. If it's a 1, I just add 16 ones, right? And then I have my inputs, my 32-bit input here. It comes out of the register. Now we have our two 32-bit inputs. And this is our ALU. And the typical logic function, logic symbol for an ALU is this weird looking Pac-Man type thing, right? And then you add them together, and that gives you your data memory location. So you have A of 0, and then you add the value in the immediate, and that takes you to your actual A of 5. So that's what a pointer actually is saying. The memory location is there. Okay, the fourth one is what's known as PC relative. PC relative means that PC stands for program counter. And what this means is this is what we're knowing as branching, meaning I am at a certain instruction, and let's say I have some sort of if statement. If A equals B, do this code. We determine that A does not equal B. Therefore, we do not want to do that code, right? So let's say the code was 5 instructions. I need to skip those 5 instructions and get to the thing after the brackets, right? That is what's known as a branching. And so the branching, the immediate value is, tell me that value would be 5, right? I need to go 5 more instructions. And then here we have program counter, we have an adder, and we have the number 4. Now, the reason we have the number 4 there is because of byte addressing. So how long is an instruction in MIPS? 32 bits, right? And what type of addressing did we use in MIPS? It's one of those like, oh, he just said this like 5 minutes ago. Starts with a B. No, not base. That's not base addressing. Is this here? Remember byte addressing? So what's 32 divided by 4? 32 divided by 8. Sorry, 4, right? So we have to represent 4 blocks of bytes to represent one instruction. Therefore, we have to, every time I want to get to the next instruction, I don't add 1, I have to add 4. Does that make sense? So PC plus 4 gives me the next instruction. So then what happens here is let's say I need to go past 5 here, right? I do sign extension, I have 32 bits. So this here stands for shift left 2. It's an actual physical value that shifts left by 2. Why do you think I need to do that? I alluded to it a little earlier. I'm not sure. Who's the person who answered my question about multiplying by 8? So what am I doing here? 4, right? So this becomes 20. Now, why would I want to multiply by 4? We just did the math problem a little earlier. Because every address has 4 bytes. So in order to get to the 5th instruction, I have to multiply by 4. So therefore, it becomes 20. So this becomes 1 plus 20, 4 plus 20, so 24. We get to the 6th instruction, which happens to be the instruction after the branch for the F statement. Does that make sense? That's why we do it. You add them together, and then you go back to the instruction memory. That tells me where the instruction is. So the defined here, PC relative is the sum of the PC, it's a constant in the instruction. And the last one, and this is where we'll end lecture today, is known as pseudo-direct. Pseudo-direct is when we jump. So branching, we have to determine how many instructions we're going to go past to figure that value. That's why we have to do an addition here. So program counter, PC plus 4. This is plus 4 again here. So I'm going to zoom out. Let me read the definition. The jump address is the 26 bits of the instruction concatenated with the 4 most significant bits of the program counter. So what does concatenation mean? Does anybody know what concatenation means? Okay, so concatenation means I can take the 4, let's say this is 0, 1, 0, 0 is the 4 most significant bits of the program counter. I can copy these 4 and append them to the front of your 26 bits. So that's known as concatenation. And the symbol for concatenation is this guy right here. It's a circle with a line straight up and down like that. So here's what's happening. You have a jump instruction. You take those last 26 bits. You multiply by 4 because each address requires 4. So now you have the base addressing value. So this says 26 in here. Shift left 2, SL2 makes everything much easier. This becomes 28. We need 4 more bits. So we take the PC plus 4 here. So if you look in your data path sections of the textbook, you'll see PC plus 4. You have this come in, you concatenate it. The 4 most significant bits of this new program counter become the 4 significant bits of your pseudo-direct instruction. So now this is 32 bits out here, and that goes to your instruction memory because that's the next instruction you're going to use. And to tie that in there, if you were doing a function, you would store the value of the register in bit register 31. Then you do something called a jump register instruction, which is actually an R-type instruction. But you get that value, you get the 26 bits, you can shift left by 2, then you concatenate the 4 most significant bits of the program counters we've done here, and that allows you to actually jump. So those are the five types of how we actually represent values in memory in a computer. Does anybody have any questions about that? Well, on that note, you're dismissed.